Hey everybody, hope you enjoyed the last week that we talked about frictional force and our snow tires. Today we're going to be talking about tension force and body problems that have more than one specific entity. Remember that tension force is the force on a rope or a string on an object. The direction of that force is always away from the surface of the object, which just means, so if I have a box and I pull it with a 500 Newton force, we're assuming that that force is always going away from the block. When we're dealing with ropes, we need to assume three major things. So the string experiences no friction, so we're going to deal with some situations where it has to go over a pulley. And when it goes over a pulley, it changes direction, but it doesn't stretch or experience any friction. Okay, so in this example here on the right, we have a block. Let's say that it is 3 kilograms. Okay, and just for the purpose of this, I'm going to assume that gravity is 10 meters per second squared, not 9.81, because I don't want to use a calculator. So in this case, we have this tension force up here, Ft, being balanced by Fg. That Fg and Ft, we know we're going to be equal because in this situation, it's not even moving at all, right? It's just a mass standing still. So in this case, our F net is just going to equal Fg minus Ft. So in this case, I have down as positive. So if F net is 0, we know that Ft has to be equal to Fg, so the tension force in this string is just going to be 30 newtons. So here's the example of the multi-body problems, right? We have two masses that are attached to the roof. And so we're going to have two different tension forces, right? This force of tension 1 and this force of tension 2. Okay, this one's relatively straightforward because we know that F net is equal to 0. So in these problems, we're going to have to start looking at these as multi-masses as a system together, so both objects together, and then we're going to have to look at them individually. And I'll show you what that means later. Okay? And so there are two ways to deal with these. The first one is what we're going to use primarily, so we're going to analyze the net forces for the system as a whole. And so what that means is when we are dealing with multiple bodies, we're going to add them all together first and find out the acceleration of the entire system. Because we know, because these two masses here are attached by the same string, this mass, let's say for example, is accelerating at 1 meter per second squared. We know that this mass, if it is accelerating at 1 meters per second squared, because it's attached to a string, this has to also be going at 1 meter per second squared. Same with this example. If this is going at 2 meters per second squared down, we have to assume that this mass 1 is going at 2 meters per second squared up. Okay, and so the whole goal of this process is to find that number, find the acceleration number for the entire system. Okay, and there's two ways to do that. Find the redraw it as one whole system, which I'll show you how to do later, and then we're going to find the acceleration and then plug it into each individual block. Or we can analyze each piece separately and then substitute them and eliminate them in algebra, but we're going to always use number 1. Okay, and so one more note is that when we find the acceleration of the whole system, we're going to need to make the force of tension internal. which means we're basically going to completely disregard the rope for the first part of the question, and then the second part, we're going to add it in. Okay? So, this first one, we have 3 masses hanging on a string. We know that F net is equal to 0 because it's not moving at all. Okay? And so all we can do is this very first mass here, this rope FT1, FT2, and FT3. So we know that this tension force for the first block is the same as, we're going to redraw the system, as 30, 50, so a 60 kilogram block. Okay, so if we ignore these two forces of tension and redraw it, this tension force, or FT1, is just going to be equal to Fg of this big 60 kilogram mass because we made all the forces internal. Okay, so in this case, if we do (60 times 9.81), we know that that is going to be equal to 588.6 newtons. All right, so the tension force in this FT1 is 588.6. Then we can just redraw again and say, okay, this has a 50 kilogram mass on it. We can say 50 times 9.81, and that's going to give us 490.5 newtons. Okay? And once again, this 50 number comes from adding M2 and M3 together. And then thirdly, we can just find this last one. A 30 kilogram mass has an FT3 of just 294.3 newtons. Okay? That's just 30 times 9.81. All right, so basically in these questions, we're redrawing and drawing different situations to find the force of tension as blocks increase or decrease. So here's another good question. 2 sleds are tied together and pulled eastward across an icy surface with an applied force of 120 newtons. The mass of sled 1 is 12 kilograms and the mass of sled 2 is 8 kilograms. Assume that no friction acts on the sleds and determine the FT in the rope. Determine the acceleration. So I'm going to say, so we just have one FT right here in this rope. Okay, and we know, and the main point of these, the way to problem solve these, is we know that sled 1 and sled 2 have the exact same acceleration. There is no friction on this, so that makes it super easy, which is good. So I'm just going to add a sticky because I don't really have a lot of space here. So I'm just going to redraw it. So we have sled 1 and sled 2 that are 12 and 8 kilograms respectively, okay? Oops. So why is this doing this? Okay, so we have 12, and that's on the front, being pulled by 120 newtons. And then this rope FT, and then an 8 kilogram sled. There's no friction, so there's just this force of tension in between. And then this applied force right here. Okay, it's applied by a rope, chain, whatever, or it's just being pulled. So the first step we're going to do is we're going to redraw. So step 1, we're going to redraw the free body diagram. of the system by making Ft an internal force. Okay, and because it's an internal force, that just means that we're able to ignore it. Okay? So what I'm saying is we can go like this and say, okay, this 20 kilogram mass, which is both sleds acted together, are being pulled by 120 Newton force. Okay? So the purpose of this step is that now I can find the acceleration of both sleds. So F net is just equal to that applied force of 120 newtons. So that 20 times the acceleration which we're solving for is equal to 120. So the acceleration is just going to be 120 divided by 20, which gives us a nice number of 6 meters per second squared. Okay, so now we know that the entire system, which is both sleds together, are going to be equal to, oops, sorry everybody. So we know that both sleds are moving at 6 meters per second forward. So now we can look at each individual block. So I'm just going to use sled 2, which is an 8 kilogram block, and that's being pulled by Ft. And so we know that this is moving at 6 meters per second. So now I just go that F net is equal to Ft, because it's no longer an internal force when we look at each block individually. And then this Ft, so 8 times 6, because we know that it's moving at 6 meters per second, is equal to Ft. 6 times 8 is just 48 newtons, okay? So now we know that that tension force is equal to 48 newtons. And that's the end of the question. However, there are two ways to get this 48 number. One is a lot easier, one is a lot harder. Even if we look at this 12 kilogram block, the tension force should equal 48 newtons. So we have the 12 kilogram block is being pulled this way by tension and this way by Fa. And so I know that F net is going to equal 120 newtons minus the force of tension. I also know that 12 times 6 equals 120 minus Ft. So I can rearrange this and say that Ft is equal to 120 minus 12 times 6, which is 72, also equals 48 newtons. That's excellent, because both ways were able to get us the same answer, and we know from our very first thing that the tension force put on two objects, this Ft at this junction will be the same as Ft at this junction. So all is right with the physics world, and then we are good. Just pause here for a second. Okay, one more example. I suggest you pause the video here and try this on your own, because it's a very, very similar problem, except for the only thing we do is we're adding friction. Okay, so pause it here, try this one on your own, and then come back in as long as you take, and then we'll take it up. And we're back. Good. Okay, so this one, we're going to do it in the exact same way. The only difference is that we're going to have a frictional force here. So first step is going to be to redraw. So we're going to redraw this as being pulled. 3 plus 7 is just 10 kilograms. Being pulled by 25 newtons and held back by this frictional force FF. Now we don't know that value yet, but we can, just to the side, we know that the force of friction is just equal to mu K Fn. And in this case, mu K is 0.12 times the normal force, which is 10 times 9.81. So that gives us a frictional force of 11.77 newtons. So if we go back to this F net, we know that F net for the entire system right now is equal to FA, or the applied force of 25 newtons, minus the force of friction. So in this case, if we have 10A is equal to 25 minus 11.75, the acceleration gives us a value of 1.32 meters per second squared. So we know that both the 3 kilogram block and the 7 kilogram block are moving at 1.32 meters per second squared. So using that same thing as last time, I'm going to look at the 3 kilogram block by itself. That's being pulled this way by this force of tension. Just the rope, not the 25 newtons. We're trying to find that. And then the force of friction on just the 3 kilogram block. This is an important part. Don't just say, okay, I've already done this calculation and put this 11.75 in, because this force of friction only pertains to the force of friction on this 3 kilogram block. So we're going to have to redo that calculation, where force of friction is just going to equal 0.12 times 3 times 9.81, which is the normal force. And so in that case, that gives us 3.53 newtons of frictional force. Then we go back to our F net, where F net is just equal to Ft minus Ff. So in this case, 25 newtons minus 3.52 newtons, 0.53 newtons, gives us a net force of 7 point, no, that's not right. What have I done here? Oh, sorry. Apologies. So 3 times 1.32 is equal to force of tension. This force of friction isn't 3.53. This is 25 newtons. Is it? Oh, man. Okay. Calculator. Sorry. Three times 9.81 times 0.12. Yeah, 3.53. I was right the whole time. Sorry. I need to have more confidence in myself. .53 newtons. All right, so let's go back and restart here. 3 times 1.32 is just going to be equal to this force of tension, which we're trying to find, minus 3.53. So 3 times 1.32 is just 3.96. So 3.96 newtons plus 3.53 newtons gives us this force of tension. And in that case, that force of tension ends up being 7.5 newtons. And once again, we can double check this answer by looking at the 12 kilogram or the 7 kilogram block. That 7 kilogram block has this FT on it, also has FF on it, and then has this 25 Newton force on it. This frictional force is going to be 7 times 9.81 times 0.12, so 8.24 newtons. So our F net is going to be this 25 newtons because it's going forward, minus the force of tension, which we're trying to find, minus 8.24 newtons. So 7 times 1.32 plus 8.24 minus 25 newtons gives us negative FT. And remember, the negative doesn't really matter. That's just the direction. So 7 times 1.32, 9.24. So 9.24 newtons plus 8.24 minus 25 equals negative FT. So FT is still going to equal 7.5 newtons. This is going to be negative, but we're going to divide by minus 1. Okay? So that's multi-step problem. So in summary, we need to redraw the FBD as 1. Then we need to find acceleration of the whole system. Then we're going to look at each individual block to find FT. Okay? This one is very similar. A couple of hints. These ones we're going to do both of these style here. They're different from the sled, in which case that they're not pulled by anything. The only thing that they're pulling down is FG. Okay? And so in these ones, you follow the exact same steps, but if you want, and it's helpful, you can kind of bend these ropes with your mind and make them flat like the sled examples that we just did. So in this one, let's say this is being held back by a force of friction. First step, we're going to redraw this whole thing. Okay, so M2 and M1. M2 is being pulled by FG. There's an FT in the middle, which is the rope, and then this is being held back by FF. So, just like the sled problems now, we're going to redraw as M1 plus M2 being pulled by FG and held back by the frictional force on M1. We find acceleration, then we can find the tension. Same with this one. We can bend this with our mind into a flat line. M1, FT, M2. And this one is just being pulled by FG of M2. And this one is being pulled by FG of M1. Then we redraw as a total block, M1 plus M2. Find the acceleration, then look at each block individually. Okay? Please complete the homework provided and get your sled problems in. We're going to be doing one more concept and then a unit test. So there will be a quiz on Friday next week, and then a unit test all week the next week for dynamics. Thank you very much. Bye.